Okay, here we are back, trying to understand how the transformer model works. Let's just quickly check that this is working. Okay, yeah, the stream is working. Great. So, last time we basically went through the attention mechanism and looked at what's computed here, took a look at these different parameters, and I just want to take a quick look at Carpathy's code here to see if there's anything to learn from that before moving on to the rest of the paper. Just got myself some chocolate for support. Okay, this is the bit oh, flash attention. Okay, this is a different. This is just another, I think, trick for more efficiency, so we'll skip that. Okay, so queries at the at symbol is the matrix multiplication, right? So, well, I guess this is basically just yeah, okay, I guess this code is exactly the same here. This bit is exactly the same as where is it? As it is essentially this equation here, and then I guess with multiple heads that this is just probably implicit in the dimension of these KQ and V in this code. Patch size, sequence length, embedding dimensionality. Where is number of heads? Number of heads, number of heads. I mean, maybe this is just one head here. Well, I guess maybe this is just one head. Well, there's number of head here. And it kind of splits this into three or four-dimensional matrices here, where the dimensions are the batch size, sequence length, number of heads, embedding dimensionality, split up by, so again here I think he also does split up the input data space into equal parts for each head. And then C underbar attention is linear layer Okay, I guess because the number of heads times the dimension of the, so the dimension dk dv times the number of heads is the dimension of the model. Also, then he can just do one linear layer here that is the dimension of the model. Is that right? Probably is. And embedding, yeah, so that is the size of the input. And then there's three copies of it, right? So yeah, right. So it's basically make a matrix that's size of the input times 3 times size of the input. So you get size of input squared, and then 3 copies that you need here. And then because of the way that the dv, dk, and the number of heads are chosen, you can then just divide that equally among the heads. And so here he can create this view that just splits that one giant linear layer up into so it's basically, in the beginning, it's just one giant linear layer that has everything in it, and then he splits that up into sort of bits, into smaller pieces that belong to V layer 1, V layer 2, V layer 3, K layer 1, K head number 1, K head number 2, K head number 3, Q head number 1, Q head number 2, Q head number 3, and just construct all of these different bits that you see in this picture here from one large initial linear layer, right? But then what it does here is, I think, even in terms of dimensionality and everything else, is exactly the same as what we see here. It's just written in a different way. Hope that makes sense. I hope I understand this correctly, but I think that should be right. Okay, so then moving on. Applications of attention to our model. In our model, the transformer uses multi-head attention in 3 different ways. 1, in encoder-decoder attention layers. The queries come from the previous decode layer, and the memory keys and values from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanisms in sequence-to-sequence models, such as citation. Okay, number 2, the encoder contains self-attention layers. In a self-attention layer, all of the keys, values, and queries come from the same place. In this case, the output of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up and to and including the position. We need to prevent leftward information flow in the decoder to preserve the autoregressive property. We implement this inside of scale.product intention by masking out all values in the input of the softmax, which correspond to illegal connections. So this is just explaining the slight difference between the 3 attention mechanisms that are in this diagram. The first one that was mentioned is this part. So this one has inputs from this this encoder mechanism, and from whatever comes out here in the decoder bit. Then the second one is this one here. So this is just internal. So this takes 3 copies of the same input and just looks at the input within the encoder. And then there's this third one here that's the same. It's just an internal attention mechanism, but that is masked so that it can't look at sequences that come later in the sequence. It can't look at tokens that come later in the sequence. I mean, this kind of does make sense to me, that this one kind of encodes input in one language. This one is trying to figure out what is the next token based on what I've said so far, and what sort of the representation of the input is. Like if you at training time, okay, sure, you can look at the whole example, but at prediction time, when you want to actually translate something, you don't know what the right answer is, right? At inference time, so you know what the input sentence is, so you can look at everything. You know what sentence you've constructed so far in terms of translation, but you don't. The thing you're trying to predict is everything that comes after that, right? So it doesn't really make sense to allow this at training time to look at tokens that come, token of the target language that come after the token that you're looking at right now, right? So I think this, to me, makes sense, but I'm not really sure what the effect would be if you didn't mask this here, right? Like it seems to me then at prediction time, you would try to predict something with where in the input here you get values that don't make sense, right? You don't have access to the whole bit of information, so you would have to, even though it was trained on looking at the whole information, you would have to give it like some, nonsensical values basically, and then maybe it just doesn't work as well. But like this bit would still work, this bit would still work, and instead of half of this bit would still work. So maybe, I guess what I'm not sure is, if you don't do this masking here, does the whole thing come apart? Or does it, like, can it still do translation? It just doesn't work very well, right? Is this more of a, okay, the basic functionality is still there, it just degrades? Or is the masking key for this whole thing to work? That I'm not entirely sure. And at least intuitively, it feels to me like if you don't mask and you give it nonsensical values at prediction time, then like probably it will do something that's not too bad, but like it will generate tokens that maybe that maybe reflects something of the distribution, but maybe it's kind of below the threshold of what is humanly recognizable as speech. I don't know. That would be my guess. That sort of it mimics we should still be able to mimic the distribution, but it's probably at a level where you wouldn't really think that it's useful. That would be my guess. Or maybe maybe it does have useful output that a human can recognize as useful. It's just not. It just doesn't have great performance. Don't know. Would be interesting to know. Okay, so that was just a comment on these different variations for attention. Position-wise feed-forward networks. In addition to attention sublayers, each of the layers in our encoder and decoder contains a fully connected feed-forward network, which is applied to each position separately and identically. So, I mean, I don't know why they say this, but it's just a fully connected network, I guess, right? Fully connected layer. This consists of two linear transformations with ReLU activation in between. Two linear transformations with ReLU activation in between. While the linear transformations are the same across different positions, they use different parameters from layer to layer. Another way of describing this is two convolutions with kernel size 1. And okay, that really doesn't make any sense. I'm not super familiar with the literature, but convolution kernel size 1 probably just means linear, so I don't know why they need to rephrase it like that. Is that right? Maybe you should ask ChatGPT. Convolution of kernel size 1. And 1 by 1 doesn't really make sense. It's like d by 1, right? And 1 by 1 convolution at least seems to do something. Well, I mean, there is okay, linear here, but then this is max. Oh, okay, yeah, this is just the ReLU. Not sure, but it seems like this is using more words than necessary, maybe. The dimensionality of input and output is 512, so the full model dimension, and the inner layer has dimension TTFF. Okay. Why is that? So why is that exactly 4 times this? I mean, these must be these two matrices, right? So this is like, in order for this to make sense, this must be at least 512 along one side, and then there's another 512 here. Then why would you have... Oh, okay, so yeah, right. So this is 512, this is 512, this is 512, this is 512 parameters. Yeah, so I think this is just 512 by 1, 512 by 1 transposed, 512 by 1, 512 by 1 transposed. I mean, depending on how you think about vectors, but, or arrays, I think is a more correct term, but yeah, I think that's it. Okay, let's put that here. I don't think we need to look at this. This is just that. It's just giving it more parameters. DFF, yeah. Embeddings and softmax. So okay, maybe just sorry, I'm jumping around a little bit, but just to make sure that this is understood. But position-wise feed forward, if I am correct, is are these blue boxes here, right? So these are just linear feed forward parts. So we've understood basically. We looked at the multi-head attention bit, like it has slightly different variations with different inputs and this masking, but we've looked at this, we've looked at what this layer norm does, we understand what this arrow that sort of goes around the orange box does, and when it says add a norm, we understand, okay, this is from the layer norm. We understand, okay, what goes in here are 3 copies of the input, same here, and then here it's slightly mixed, but it's kind of the same. We understand basically this middle piece here, and then okay, output has a linear layer and softmax. I think that probably don't need to explain. But then what we don't understand yet is input, these reddish boxes, input embedding, output embedding, how they do that we don't know yet, and then how they do this position encoding we don't know yet. And so now we're looking at the red boxes, I think. Done this. Okay, similar to other sequence transduction models, we use learned embeddings to convert the input tokens and output tokens to vectors of dimension D model. Okay, so I think before moving on, that makes sense to me. We just need to find out how we learn this embedding. But so there's a vocabulary that you have, that the text that is input is comprised of words or usually they use what's called a token, so like a sub piece of words maybe. But there's at least in the input data, there's a fixed number of these words. I mean, even if you can just think about it as letters. Okay, let's just think letters, or letters. Let's say, or I don't know, characters, right? There's a fixed set of characters that's being used, and so if you have 50,000 different characters, or the whole Unicode spectrum, let's say, then that's the number of characters. So when encoding that into some sort of input value, you can potentially have, if you do something like one hot encoding 50,000 dimensional vectors, and I think the embedding will compress something like that down to a smaller vector space where the characters also don't have to necessarily lie along one of the dimensions, but the tokens kind of, they get distributed in this smaller vector space in some useful way, I think. Anyway, let's keep going. We also use the usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. In our model, we share the same weight matrix between the two embedding layers and the pre-softmax linear transformation. Between the two embedding layers. In our model, we share the same weight matrix between the two embedding layers. Why is it two embedding layers? And the pre-softmax linear transformation. Not sure I understand this yet, but I mean, I think this just says that if you create some kind of embedding here, you need to know what that embedding is and use it here to reverse it, to go back to tokens that you can read, to figure out, okay, what character is it predicting, and not what, what thing in the embedded space is it predicting, I think. Let's look at this code. Oh, okay, so it uses what? Is this like a standard technique then? Just like this embedding? So, I mean, this looks like, so because they're using, so they're saying just use this class from PyTorch, vocab size, model size. So vocab, whatever, 50,000 characters, 512 dimensional model. And then the forward for this is just do the embedding and then scale it a little bit. So basically all of the work is done by this class, because they're using this. Seems to me like maybe this is, maybe there's a lot more logic and knowledge packed into these red boxes than I expected. I thought, okay, this is maybe just some, something like this where we can just write down some matrix multiplications and then this will be trained somehow, but maybe this is a bit more. Be right back. Okay, so let's understand what this embedding component here is doing. Learnable weights of the module of shape. Okay, so I guess what they're saying here is, okay, they train some sort of maybe they train some sort of matrix that takes vectors from the vocabulary size dimension to embedding dimension. And then probably you can kind of somehow, I guess it does that in a way that is semi-reversible. Not reversible, obviously, but I'm guessing the dimensions, the components in this matrix are somehow linearly independent, maybe. So it creates this vector space of that size. But how does it know how to do that? I mean, is it just like you put this matrix in between and then it's like an autoencoder or something? I mean, without, I guess, the right bit here is just like this kind of encoder bit. Is that all it is? Well, I guess, I mean, if kind of in the end we go back to the dimension of the vocabulary size, then this whole thing is kind of an encoder, I guess. Maybe that's why it's called that, I guess. But wait, going back to the documentation here. Containing 10 tensors of size 3. 1, 2, 3. Okay, this makes 0 sense to me. Like, how would it know how to do this without some form of training? It does say that it trains it, right? Learnable weights. I guess this is just initialized. Okay, this is maybe just the initialized value. Initialized from, this is, I don't know what this is, but I think this is just like a normal distribution. So it's like a normally distributed. Maybe I mean some random initialization maybe. So I guess this is what this is. I mean, isn't there some kind of literature link here? Source code, maybe this has some kind of literature link. I mean, maybe this is as simple as it is. Let's just quickly kind of scroll through it. I mean, it seems very short. That's good. Okay, and the embedding is just another module. Okay, this is just the documentation. So this doesn't have any new information that's not already in the documentation. Padding. Okay, parameters. It has this. It's just like one parameter matrix. Here, okay, return. Aha. What? Self, weights, padding, maximum, blah, blah, blah. Okay, so this one is again the functional bit that we've seen at some point. Where is this functional F? So, torch functional embedding. Okay, but that's the same. That's the same thing. This is like just, is that not the same? Basically, class is just a class, and it just does this when it's called. And this torch.embedding. I don't know. What is a torch embedding? A space with low dimensions where high dimensional vectors can be translated easily so that models can be reused on new problems and can be solved easily. Okay. I mean, I guess you could watch this 20-minute video now. Because I'm not the only person that isn't sure how this works. Except this person thought about this 3 years ago. So let's look at this source code first. No, let's get some more context before we look at C++ source code. Okay. Okay, other people are using an embedding just like that. I don't understand. I don't understand how this works. I read the documents, but I still don't understand. Yeah, I mean, that's me right now. Yeah, so this is just like naive, first of all, encoding of tokens, right? So this is a sentence one, yeah. So we just do that, but we want to do this more efficiently, so that's why we use the embedding, right? I think concept-wise it's clear. Or maybe there are like some heuristics of how you can do this, how you can create these embeddings in sort of a useful way. But I don't know. Maybe there's some kind of mixing of dimensions that generally gives a good. Then then it would sort of depend on like the order in which you feed in the, like it would then depend on. I always thought of like embedding as something like word to vec, right? Where the lower dimensional vector space, the distances between the vectors have some sort of meaning, like similar words end up in similar areas of the vector space, but maybe that's not the case. Maybe this is just some sort of clever mixing of dimensions that lets you sort of downsample this to something that isn't like a 50,000 dimensional vector space, right? So maybe so that the input, if you use sort of this naive encoding here, the input matrix would be really sparse, right? Would it? Yeah, I'm not sure. I mean, if you do some sort of one-hot encoding somewhere, it would be super sparse. So maybe this is just some clever random mixing of dimensions that allows you, like I said, to downsample and like be more efficient rather than anything learned, like rather than this sort of embedding of meaning already. Okay, so here they say let's do it with like one word first. 4 words, these are the 4 words that we have up here. This is a sentence, and then we do embed that in 5 dimensions. Okay. Okay, so somehow this word that's encoded as 0 gets then represented as this 5-dimensional space without any training, right? And then if you use this as a sentence and encode that as 0, 1, 2, 3, you get these 4 different vectors. This is a sentence. Is this a sentence? Okay, we have these 2 different sentences encoded like this. We ask the thing, can you give me the embedding? Okay, it does that predictably. Sure, okay. Okay, because there's no training. I mean, this has to be some sort of clever downsampling trick. Okay, I think we've got the gist from this one. I don't want to do this. Embedding. Okay, there's a to-do here, or is this like, I guess this isn't really the latest commit. Some random commit. Yeah. Can't we just do master? Master. Isn't there like a master branch? Main. Okay, let's do that. Okay, I guess this version is more complicated. There's like more words I don't understand. And it's also slightly longer maybe. Let's go back to the earlier version that this person from Stack Overflow linked to, where there's only like 100 lines less code. Okay, maybe this we'll get the idea, maybe not. But I mean, my understanding right now would be that it's a clever downsampling trick. Maybe. Let's see if there's some evidence for that. What? Weight index select. I mean, I guess this one just does the embedding and this one does the reverse. Like, how does it? Oh, is it maybe just like it's not even learned? It's just it does Gaussian. It does some sort of Gaussian random matrix and then that works. And then that's trained. I mean, why not, right? Then that would be like it's a sort of a random mix of the dimensions, and then these parameters can be learned and optimized. I mean, maybe that could work. Like, why not? I mean, maybe that's all it is, right? I mean, looking at this, it seems like that's what it is. Okay, yeah, I've used this a long time ago. Man, this is like a 50-year-old library, right? I think. Yeah, this is like a Fortran library that's used everywhere. Sorry, I'm going off on tangents and tangents. Yeah, this is from, okay, maybe not. Oh, well, I guess it's 2023, so, you know, this is like 30 years. Okay, like whoever maintains and wrote this. This like giant impact. Well, like who's the author of this, huh? Author. Proper credit be given to the authors. Okay, but who are you guys? University of Tennessee. Okay. I mean, I guess it does have GitHub, so anyway, I mean, kudos to these guys. Here you are. Well, I'm assuming this doesn't have all of the contributors since 1992, but yeah. Wow, look at this guy. This lady right here. University of... Wow, I mean, kudos to her and the team. Thank you. Okay, that hasn't really answered my question on like what this embedding does, but it seems like it's just a smart trick to downsample to a lower dimensional space, and then you can optimize from there, I guess. Okay. Got that. Oh, wait. Maybe this is even the right paper. Using the output embedding to improve language models. We study the topmost weight matrix of neural network language models. We show that this matrix constitutes a valid word embedding. When training language models, we recommend tying the input embedding to this output embedding. We analyze the results, update rules, and show that the tied embedding evolves in a more similar way to the output embedding than to the input embedding in the untied model. Okay, so I guess we also offer a new method of regularizing the output embedding. Our methods lead to a significant reduction in perplexity, as we are able to show on a variety of neural network language models. Finally, we show that weight tying can reduce the size of neural translation models to less than half of their original size without harming their performance. Okay, so I guess this is saying if you have like some sort of linear thing at the beginning and something at the end, you always get some sort of embedding that's a valid embedding at the end if you train the model correctly. And then if you make these two, the beginning one and the end one, if you connect them and make them be the same, that can improve training and results, and you still get a valid embedding. And so that's also what they're doing in this paper. Okay, let's move on. I think we've got the gist of what this is doing. Maybe let's take a quick look at what Carpathy is doing here. Yeah, he's also just using the torch implementation, right? Yeah, makes sense. Okay, not different from what we have here. Okay, finally, missing piece, last missing piece in this diagram, I think. Last missing piece. So we just discussed this red box, and now we discuss this sort of yin and yang symbol here, positional encoding, position encoding. Why are they adding that there? I don't know, maybe they'll explain and how they're doing it. Since our model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in this sequence. Okay, I guess this makes sense, right? The model looks at a sequence that is ordered, but the attention heads can look anywhere they want, so they don't really, they don't really see position, right? And so there's no implicit, I mean, apart from like the size of the window you're looking at, apart from this model dimension, and like the masking that's done, there isn't any implicit information on, okay, this token comes after this, after this, after this. And so they're adding this back somehow. Yeah, again, sorry, I should probably just keep reading, but this seems like something that you could probably leave out, and you would still get like something that can produce something that's viable, like that can still maybe do the translation task in a good way. But maybe this just improves performance. It would be, again, interesting to see how this improves. Like if this is like a necessary thing, if the whole thing crumbles if you take this out, or if this is like an incremental improvement. So we add positional encodings to the input embeddings at the bottom of the encoder and decoder stacks. The positional encodings have the dimension the model. So this is after the embedding, same as the embeddings, so that the two can be summed. So basically you modify, like, okay, you've got the embedding, and you perturb each of the values a little bit with some kind of positional information. Okay, and then sometimes you can learn those, sometimes you can fix it. In this work we use sine and cosine functions of different frequency. Okay, so these are like fixed positional encodings. Each dimension of the positional encoding corresponds to a sinusoid. The wavelength form a geometric progression. Okay, I'm guessing this paper up here explains why this is a good idea. We choose this function because we hypothesized it would allow the model to easily learn to attend by relative position, since for any fixed offset k, this thing can be represented as a linear function of that. So k plus k is a linear function of the other ones. Yeah, okay. In addition, we apply dropout to the sums of the embedding and the positional encoding in both the encode and decoder stacks. For the base model, we use 10% dropout rate. Okay. Again, this seems like just something that, well, it's not really clear why, but it just works better. I mean, it makes sense that, you know, you have to add, that you have to give the model some sort of information on the positions, because otherwise it doesn't have that. And so it's you know, it's kind of, I think, evident that adding that will improve the model performance. But why does adding this information as a perturbation on top of the embeddings in this form make it better? Not entirely clear to me. Okay, so below the positional encoding, we'll add in a sine wave based on position. The frequency and offset of the wave is different for each dimension. Yeah, okay, I mean, this is just, okay, this is what the sine functions look like based on the dimension and the position in the token. You get, I mean, with these sine functions, I don't know, you probably get like some, they probably have like some useful properties that, like, each of them is kind of independent of the other one. So, you know, you truly add the positional information back to it, not just some sort of distorted version of it. Like, you can probably reconstruct, if you knew what the, yeah, if you know what the perturbation values are, you can one-to-one reconstruct this position information from this, right? I think it's not like, okay, you know, we're giving you a low level, not low level, we're giving you like a low quality version of position information, and you can use it a little bit. Like, these sine functions encode the position information in a unique way, and you can reconstruct the position from knowing what this value was, I think. Maybe, or at least up to some frequency. But yeah, so there's maybe some good reason for learned position. Oh yeah, okay, I guess here again they say we also experimented with using learned positional embedding and found that the two versions produced nearly identical results. We choose the sinusoidal version because it may allow the model to extrapolate to sequence lengths longer than the ones encountered during training. Let me just turn on the light. Okay, but I mean, I guess in terms of the model, that's nice because I'm assuming, okay, so this does improve performance, but this doesn't add any parameters to the model at all. So in terms of the logic and the architecture of how the model is set up, no change, no parameters to learn. It's just a trick that we add. And then we've got the full architecture now with all of the pieces, and then this code just puts it all together. Okay, and so this just constructs all of the pieces from these helper functions that we've defined so far. These are just all the helper functions that we've seen. So basically just, yeah, what is generator again? Generator. What's generator? mean, this bit I remember, this bit I remember. This is just a box around the left and the right hand side of the diagram, right? With these attention bits inside, and embedding, positional encoding. These are the where the information. This is the bottom of the diagram, right? And then what is generator? Linear and softmax. Okay, yeah, that's just the end bit. Okay, yeah, sure. I don't know why they call this generator, but it's probably a technical term from the literature. But yeah, so this is just putting all of the pieces together into one big model. And then they initialize the parameters in some, what? Okay, I mean, here it just says comment. This was important in their code. This was important in their code. Gloro. What? Fan. Average fan. No. What? Gloro. Is this like a typo? Initialize. But why? It doesn't say anything about initializing the values. Xavier uniform. Failsafe tensor with values according to the method described in understanding the difficulty of training deep forward neural networks. Okay. Well, this isn't even quoted here, no? Cited, sorry. Understanding the difficulty? No? Maybe this is supposed to say this was imported from their code. And just says, okay, this is what they did in their code, so I put it here. Oops. Oops. Maybe this is just a typo. Attention is all you need. Did they have a repository with code along with this? Repository, no, code. Code base. Attention is all you need. Repository. Well, many people seem to be reproducing the code, so not clear that there was a code available. Anyway, I mean, seems like this is like some sort of standard maybe way of initializing. Inference. Here we make a forward step to generate prediction of the model. We try to use our transformer to memorize the input. As you will see, the output is randomly generated due to the fact that the model is not trained yet. I mean, yeah. Hmm. Hmm. Show example. I mean, these are just random values, but I'm not sure. Not sure what does it use as input, like why. Okay, so I guess, yeah, so it has a different random value every time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like always starts with 0. That seems kind of strange to me. Like I don't understand what this is doing. It seems like it would make sense to kind of take this as input, go through this one by one, and then predict the next token. But maybe not. Anyway, model training. This section describes the training regimen for our models. We stop for a quick interlude to introduce some of the tools needed to train a standard encoder-decoder model. First, we define a batch object that holds the source and target sentences for training, as well as constructing the masks. Yeah, so now we're getting into sort of the training. We're getting into the, and how can we make this a heading? Yeah. Okay. Now we want to batch the data. We want to, where's the loss function? Okay, this is all kind of just keeping track of stuff. Batch size. Okay. This is just a data structure to keep track of all of these parameters for training. This is like one running through one epoch of batches, probably. One batch epoch. Gives maybe some useful output, how long it took. For each batch, compute the loss, total loss, every 40 iterations, print out where we are. Finally, okay. And then the way they encode, so they have this English-German translation data set, which is probably standard thing. Maybe we can look at an example. Is there some example here? Is there not an example here? Do they not have like a sample sentence? Ah, okay. This is probably Russian and then this is English. Yeah, so it's just a data set of these kinds of example sentences. Is there not like another nice example? Okay, I mean, I'm starting to understand. Like, if you stream, I mean, there are like gaming streamers that stream for like 8 hours or something, right? That must be tiring. I'm getting tired just from like this 2 hours of streaming. Maybe I should drink some water. Anyway, what I wanted to say is So they don't use this sort of naive encoding of, okay, one character is one number, or one word is one number. They use, I don't know the specifics, but they use byte pair encoding. So basically they take 2 bytes and encode that, and then that's without you. So it's like a good, I think, from what I understand, this is like a good trade-off, right? So you don't, for this byte pair encoding, you're not encoding characters, so you're putting in more information, just a character. You understand bits of words, potentially. But it's also not like you're truly taking the word or taking word pieces. You don't understand the language you're encoding, you're just taking bytes from the string. So from what I understand, this is a good trade-off between, you don't have to learn anything about the language you're encoding, but this still works well enough and better than just using single characters. So it's like a really, it seems like a crude approximation to understanding parts of words, or like syllables, but apparently this works quite well and is easy to do. Okay. Then, okay, here's how they divide up the training data. Oh, and then they train on 8 NVIDIA P100 GPUs. Okay, I have a Mac Mini that was like a few $100 a few years ago. Maybe I can even show this. This is probably, that's what I have. So I don't think this is gonna, I don't think this is gonna finish into 3.5 days, or like even 12 hours. So maybe we can actually skip some of this training, or maybe we can just, you know, initialize random, do like training for 10 minutes, and then hope that it does something, just to see if it works. I mean, I want to see if this needs a GPU or not in the first place. What is this now? Example learning schedule. I think this is just, again, it's just a visualization, I think. This doesn't run anything, I would assume. Yeah. And then here is some way of adjusting the learning rate after warm-up period. Sure. During training we employed label smoothing. Oh, sorry, what am I doing? Oh, this is the text straight from the original paper. So they had that hardware. Not necessarily the person that wrote this code here. Well, then let's take a quick look here. So we used the Atom optimizer with these parameters. This is how they, this is the learning rate. This is how they adjust the learning rate, and then they have 4,000 warm-up steps. This part is very important. Need to train with this setup of the model. I don't know why. Okay, it doesn't really say why, but I mean, so they do this sort of ramp up of the learning rate and then slow degradation. Don't know why this would be important. Like, seems to me that, okay, whatever the shape of this is, you know, if it's like, okay, goes up and goes down, and like the number of steps where this peaks is probably roughly, you know, is kind of dependent on the size of the network, but not really sure why. Like, it seems to me like if you don't do the warm-up, if you have infinite time to train, or like long time to train, then like this, doing this doesn't make or break the whole thing, I guess. Label smoothing, this one I don't know what this is. Okay, I just want to see if this runs on my computer. Well, I guess it runs in Oh yeah, so I guess what I have doesn't really matter because I'm still on the Colab notebook. Okay, yeah, let me just skip these bits because this is just kind of about using some regularization steps. We can begin by trying out a simple copy task. Given a random set of input symbols from a small array, the goal is to generate back those symbols. Okay, this is doing a lot more than I thought. I think we'll do this in the next stream. So we'll do this example of sort of this copy task and see if the model can do that and like how long it takes to train that. Yeah, and then here they train the simple copy task. Let's see how long that takes in the next stream, and then after that real world example with that dataset that we downloaded in the first stream. There's more. Okay, a lot of this code, I'm not sure if we're going to look at this in detail. This is kind of, so these, like the way you set up the batching, etc., is key for making this run, you know, with good performance, and like even being able to train these networks, you know, without waiting for eons for the training to finish. So this is like key engineering here to make this work. But in terms of like, is it the logic of how the transformer works? No. So I'm not sure how much if we're going to look at this. I don't just want to see, you know, if we train for like a few minutes, what can it do? Is it like garbage, or does it, you know, does it look like it could go somewhere? That's what I really would like to know. But yeah, maybe let's look at that in the next stream, and then oh, I mean, maybe they even like, yeah, they even recreate some of these visualizations. That's nice. Maybe there's something interesting we'll see from these. That's nice. Oh, that's great. This is actually what I wanted to look at. Awesome. I mean, not sure this will reveal anything apart from, you know, how grammar works, but still, that's actually something I wanted to look at. So, okay, anyway, we've got all of the parts of the transformer. We're setting up batching and like the necessary scaffolding for training. And then in the next stream, we'll see whether this Google Colab instance can actually do any sort of useful training, or like whether this runs in the first place. I mean, up until now, we've just defined lots of stuff and haven't really, you know, we haven't really executed anything. So that we'll see whether that works. And then I think, yeah, we'll see whether with like minimal training on this hardware, whether anything useful comes out of it. And then, yeah, we'll leave it at that.